Welcome to Synthesis Workshop. On today's Research Spotlight episode, I'm very happy to have with us Dr. Josep Mas-Roselló, who is going to tell us about some of his work in the area of asymmetric hydrogenation. Josep graduated from the University of Valencia in 2013 with a degree in chemistry, and subsequently completed his doctoral work at the University of Bristol in the group of Professor Jonathan Claydon while collaborating with Syngenta. In 2017, Josep joined the group of Professor Nikolai Cramer, where he is currently a postdoctoral researcher. And with that, I'll hand it over to you, Josep. Thank you very much for joining us.
Thanks, Matthew, for the introduction and for inviting me here. Hi there. I'm very excited to present you the work on metal-catalyzed asymmetric hydrogenations that I conducted as postdoc in the Cramer group, as part of an industrial collaboration with the agrochemical company Syngenta. Our project began after noticing that the alkoxylamine group is present in many modern agrochemical and pharmaceuticals, such as the ones shown in here. The presence of a nitrogen-oxygen bond, colored in red, gives them unique favorable physicochemical properties. In contrast to related abundant chiral amine drugs, current NO compounds either lack chirality or are sold as racemates. However, different enantiomers frequently show differences in biological activity. Therefore, the delivery of the desired one is more efficient and sustainable. In fact, the graph below shows an increasing demand for single enantiomer drugs over the last 3 decades. In order to satisfy this demand, new efficient synthetic tools are required. In particular, the asymmetric hydrogenation of unsaturated substrates using homogeneous transition metal catalysts is one of the most practical methods for the synthesis of chiral building blocks at industrial scale. So the question was obvious. Can we produce chiral hydroxylamine derivatives via E-oxime asymmetric hydrogenation? Then, if desired, one could use known acylation chemistry to reach hydroxamate derivatives such as, for example, the fungicide adepidine shown above. Asymmetric hydrogenation of alkene, ketone, or imine substrates are established. Pioneered by the work of Noyori and Knowles, the development of chiral phosphine ligands, used in combination with different transition metals, has allowed a huge progress in the field. However, none of these catalysts have been able to selectively reduce oximes to chiral hydroxylamine products. Oximes are less reactive, and when they react, often reductive cleavage of the weak NO bond leads to undesired primary amines. Knowing this, we aimed at solving the problem by adopting a different hydrogenation approach. The lack of reactivity of oximes could be addressed by protonation with acid, activating them towards nucleophilic hydrate addition to the CN double bond. Note that the pKa of these substrates is approximately 2 units, therefore a strong acid is required. After reduction, protonation of the resulting amine basic product with a second molecule of acid may prevent catalyst poisoning, as well as undesired NO bond cleavage. This type of hydrogenations, whereby the substrate receives a proton and a hydride via an outer sphere mechanism, meaning that the substrate is not bound to the metal, are known as ionic hydrogenations. The proton and the hydride species can be generated catalytically from a cationic metal complex after dihydrogen coordination and its subsequent heterolytic splitting assisted by the conjugated base of the acid. In contrast, in classical hydrogenations, a metal dihydride is generated via oxidative addition, and upon coordination to the metal center, the substrate receives the 2 hydrogen atoms from the same catalyst entity. Extensive racemic studies at Syngenta reveal that exclusively a bent-stable iridium-3 complex bearing a capping cyclopentadienyl ligand, a lower iminorin chelate, and a labeled methensulfonate ligand was effective in this transformation, operating in the presence of stoichiometric amounts of methensulfonic acid. Remarkably, the systems show no reductive cleavage of the NO bond. At this point, we wanted to develop a chiral catalyst in order to render the reaction enantioselective, and this is how I contributed to the project. For the catalyst tests, we selected the shown aryl acetone oxime with a terbutyl ether substituent as our model substrate. We set the standard hydrogenation conditions at 1.5 equivalents of methensulfonic acid, 1 molar % of the iridium complex, 50 bar of hydrogen pressure at room temperature in isopropanol. As a reactivity reference, the achiral iridium complex shown below led to quantitative product formation. Preliminary efforts involving chiral C and chelates were frustrating, obtaining no enantioselectivity at all. The first positive result was obtained using an axially chiral cyclopentadienyl ligand originally developed by the Cramer group. Despite the modest levels of reactivity and enantiocontrol obtained, this was a proof of principle that we could bring our chiral CPX ligands out of their comfort zone of CH activation chemistry and make them control also asymmetric hydrogenations. You can find more details on the design and use of these ligands in the review cited below. Next, we tailored the CN ligand. In summary, insertion of 3,5-dimethyl groups at the aniline unit and a rigid tetralone backbone with an ethylene glycol tail proximal to the iridium center boosted the catalyst performance. In particular, the diether tail might engage in hydrogen bonding interactions with the protonated substrate. Finally, the enantioselectivity was increased to very high levels by fine-tuning the chiral CPX ligand, replacing its methoxy groups by phenyl rings. With the optimal complex in hand, we wonder how is it affecting stereocontrol in the reaction. X-ray analysis of a close analog gave us structural insights of these complexes in the solid state. In addition, one proton NMR analysis of the optimal active hydride species in deuterated THF revealed a 96:4 diastereomeric ratio of the complex provided by the chirality at the tetrasubstituted iridium center. All things considered, our hypothesis is that the chiral CP ligand orients the CN chelate, minimizing the steric repulsion between them. The ratio between the two interconverting hydride species represents the maximum achievable enantioselectivity in the reduction, which occurs through a facial selective hydride transfer to the prochiral protonated substrate. Both steric and hydrogen bonding interactions between the catalyst and the substrate may account for the facial discrimination. Next, we evaluated the influence of the solvent in the reaction. In general, alcoholic solvents gave higher reactivity, and among them, the bulky tersamyl alcohol was superior, giving excellent levels of enantioselectivity towards the S enantiomer of the product. Importantly, subjecting the Z isomer of the oxime to the best reaction conditions resulted in lower conversion and enantioselectivity. This result indicates a strong impact of the oxime EZ stereochemistry on the reaction, with the E isomer being superior. In fact, protonated oximes isomerize via solvent nucleophilic addition to the carbon sp2 and elimination. Therefore, the speed of this process can be tuned with the choice of the solvent. Not surprisingly, the less nucleophilic tersamyl alcohol led to the highest selectivity by preventing the formation of the Z isomer. The excellent enantioselectivity was maintained when using lower amounts of acid, lower catalyst loading, or performing the reaction at 1 bar of hydrogen pressure. However, with partial conversion of the E-oxime starting material. The bottom line here is the need to overcome the different behavior of the oxime E and Z diastereoisomers in the reaction in order to reach high selectivity. Oximes are typically obtained as EZ mixtures after a condensation, and the isomeric ratio depends on the substitution. For sterically biased substrates, we separated and discarded the minor Z isomer by column chromatography. We then tested different E-oximes towards enantioselective hydrogenation under slow isomerization conditions. A selection of hydroxylamine products is shown below. Remarkably, even free OH oximes are reduced without any detectable NO bond cleavage. The methoxy analog, precursor of adepidine, was formed in quantitative yield and excellent enantioselectivity. In general, the optical purity of the products can be upgraded by crystallization of their acid salts. Oximes bearing bulky alkyl substituents were also selectively reduced. Our method also provides access to novel enantiosen-rich N-alkoxy derivatives of amino acids such as the valine example shown in here. It also works with low pressure of deuterium, allowing for isotopic labeling of valuable hydroxylamine scaffolds. Oximes having similar in size substituents were conveniently hydrogenated as the untreated EZ mixtures. In this case, using more nucleophilic ethanol as solvent was optimal, favoring a faster isomeric equilibration and driving the reactions towards the R enantiomer of the products. Under these conditions, a 25-gram batch of cyclohexyl phenyl methoxyamine was obtained quantitatively in high enantioselectivity using as low as 0.05 molar% of the catalyst loading, demonstrating the scalability of the method. Remarkably, sulfur-containing heterorenes are compatible, and nitro or vinyl substituents remained untouched, showing the unique chemoselectivity and functional group tolerance of our acid-assisted hydrogenation method compared to classical hydrogenations. In summary, we made oximes succumb to asymmetric hydrogenation, keeping intact their nitrogen-oxygen bond. And this was possible thanks to the design of a chiral iridium catalyst, capable of operating at room temperature under highly acidic conditions. Of practical utility, this complex is air and moisture stable and equally accessible in both enantiomeric forms. For further details, please check out our publications shown at the top and bottom of this slide. And this successful story wouldn't have been possible without combining efforts between academia and industry. Finally, I would like to thank Nikolai and Thomas for giving me the opportunity to participate in this exciting project. Also, big thanks to Matthew for the invitation, and of course you for listening. Please contact me if you got any questions related to our project. Bye bye!
Thank you very much for watching this episode, and I hope you enjoyed Josep's talk on this research spotlight. To support this initiative, help us out by subscribing and follow us on Twitter to stay up to date. See you all next time!